Yeah, this will be an intro to the general neuromorphic engineering framework that Carver Mead and others started many years ago. In fact, the workshop, as you know, is now 30-some years in the making. And so I'll give a bit of a historical perspective and then also show where we're going, focusing on hardware. So this is related to the NIC topic, right? Neuromorphic integrated circuits. But of course, linking to all the other work groups as well. So, okay. So the field of neuromorphic engineering has been in stealth mode for many years, but it has come to the foreground, and perhaps a bit surprisingly, not the way we would have thought it to come to the foreground, but in this field of AI, that so artificial intelligence, and so for many years, everyone thought AI is not going anywhere. But then here was this game of Go, right? That was where the world champion was defeated by the machine, and machine here is Google DeepMind. And of course, this was a dramatic moment, and many of us would not have thought it'd be possible that a complex game like this could be played by a machine at great efficacy, although not a great efficiency. So just look at the power contrast here. So the human, of course, was defeated, but at what power budget? 100 watts of power is the typically just liberally accounting for the entire body of metabolism that is engaged in the game here. But still, contrasting it against the 100 kilowatts of power of the entire TensorFlow processing units in the background of the Google system, right? So power is a great discrepancy, but there's one point I should make here. We can definitely take credit as neuromorphic engineers for this advance, because actually, how did Google DeepMind succeed in doing this? For many years, AI has been about symbolic reasoning, sequential, right, thought processes, and not, in fact, the field of neural networks for many years has been the antidote to AI. But here is a time when the two start to converge. And if you go under the hood of this supposedly AI system, actually, there's a lot of deep learning based deep layered architectures, modeling, say, cortical vision or cortical information processing. Reinforcement learning is also a model of dopamine reward conditioning. So there's definitely a lot of, in fact, DeepMind, the DeepMind founders are actually neuroscientists themselves. So clearly there's a great synergy with neuroscience that actually made this happen. But yeah, power is a bit of an issue. So and so in fact, that emergence of AI, today's AI that became quite neural or neuroscience inspired, is missing at least one point of efficiency. And if you look at, sure, you get these really great improvements in say the error rate for some classification tasks. You imaged that in this example over the years, and it seems like we're going towards zero error, sure, at some exponential rate. But look at this. So the exponential rate for the cost of the operations that is taking place is on a much more dramatic exponential scale. So sure, for this 1 decade or for this one factor 10 improvement in the error rates, there's about 10 to the 8 of more operations that need to be performed, which translates to 10 to the 8 times more power. So it's extremely costly. So the exponentials here don't play to the advantage of learning. And so this has now become a serious problem to the extent that even we can make a contribution to the green, right, the ecosystem of saving the world's, I guess, our green planet by working on improving the efficiency of compute. Clearly, right, we need to do something. This doesn't scale. So energy efficiency has become a dominant factor in computing. And let's not contrast here. How efficient can we make compute? And these are just, so on the horizontal axis here, we have efficiency that can be defined. You're doing some computation, right? You're doing some operations, typically multiply cumulates or whatever they are, and it costs some energy for each of them, right? And so you can either think of the energy for each operation on this, on the axis that points to the left, which is the cost, right? So red is bad, green is good. Or the opposite scale, which is 1 over that, and that is operations per joule or operations per second per watt, same thing, right? So basically the throughput per unit power, right? So either way, those are two identical units. One is the other, or metrics, the one is the reciprocal of the other, right? And so on this scale, what is the very best we can ever do? That's given by Landauer's limit, and that's just a realization that noise will always kill us. And if you want to distinguish two states in a memory or in a compute system, right? So if you need to have two energy levels, that right? You want to have a barrier between those two states, right? That ensures that thermal noise will not just simply wash you away and destroy your state. So the barrier needs to be at least the thermal energy, which is kT, right? K is the Boltzmann constant, T is temperature. And we'll get back to this Boltzmann factor, this Boltzmann constant in a minute. So kT is a very important parameter, energy and thermal energy. And that's also, I guess, the best you can do in terms of you need to expend that amount of energy. If you only go over this barrier, go from one to the other, right? From one to the other. So that's the fundamental limits, right, of efficiency. And so the good news is this is about 10 to the minus 21 joules per operation. So that's really, I mean, very little, especially compared to not today's, but yesterday's compute systems, which are about 10 orders of magnitude worse. Right? In fact, you can argue, well, why? Wait, aren't GPU systems or FPGA systems or CPUs, for the matter, much more efficient today? Well, the main bottleneck of compute is not the actual compute itself, but the memory access, being able to actually get to the data. And the data transfer has become the dominant factor in energy. So in this case, it costs about 70 picojoules for each bit of energy to access, right, to access that bit. And so for 8 bits, that gives you about half a nanojoule per multiplied cumulative. So extremely expensive. How does the brain fare? Well, so here's a very simple estimate here. So we have, our brain consumes about 10 watts of power, estimating just from the metabolism, right? In fact, the heat that it generates. And we have 10 to the 15 synapses, depends on, right? And 10 to the, 10 to the 12 neurons, 10 to the 15 synapses. Neurons fire about, on average, 10 times per second, so it's 10 hertz. And so each time a neuron fires, all the synapses get activated. So the net throughput, if you want, there's a compute where synapses do the actual compute operations, the connections, as well as the multiply adds, if you want. So that's the product of the two. That's 10 to the 16 synaptic operations per second. Okay? And so you have 10 watts of metabolic power. So the ratio of the two, right, the ops per second per watt, is then 10 to the 15, right? And so 1 over that is going to be 10 to the minus 15 joule per operation, right? So the femtojoule per synaptic operation. So a very rough estimate, right? So clearly the brain is somewhere in between those two extremes. Now, how has digital compute fared? Well, not too much better. So all these advances in GPUs, FPGAs, etc., haven't done too much better because of the overhead of the memory. You still need to access that memory, and the best you can do is the latest advances in this GPUs and FPGAs have been this high bandwidth memory, this silicon interposers that gives you higher bandwidth access to the memory, and also a bit just only a factor 10 better energy, so that doesn't really cut it. So clearly the way to go, and that's what Carver and others were advocating, is, well, think about listen to the electrons, right? So bring the compute closer to the to the memory, or integrated to, and that's the concept of computing memory, right? And that's over the last 40 years. There have been several advances in bringing the compute inside the memory, and this massively parallel processing, right, where memories themselves compute, they're all do this in parallel, so you can get massive throughputs at low data rates, low internal data rates, but you get massive parallelism that gives you an effective throughput that is massive, right? At great efficiencies. And so this way you can get efficiencies that are close to the femtojoule per synaptic operation mark of what is happening in the human brain. You can even do better. And I'll say a few words also on this. You can actually even outsmart, I guess, or use physical principles of even getting around the energy barriers that you have in the compute, and even get rid of dynamic power that is dominant in most CMOS integrated circuits. And I'll get to that in a bit too. So that in principle can do even 10 times better than human brain, normally speaking though. So that's the framework. So where does neuromorphic engineering come in here? Well, so neuromorphic engineering is not only about the compute, what is actually being done, but also about the physical foundations of how the compute is performed. So we're getting not only at efficacy, but also at efficiency and resilience, right? So that the thought here is that if we build silicon integrated circuits that adhere to the same physical principles that we learn from neuroscience, right? Observation of how the nervous system works, then not only will we be able to compute like what happens in the brain, but also we'll be doing this in a fashion that is as efficient and as resilient as the natural intelligent systems. And learning and adaptation are key to getting that extreme efficiency, owing to the fact that learning can get around the natural imprecisions that we have. In fact, there is a beautiful book by John von Neumann, and we all know John von Neumann as the father of digital systems architecture, digital computing. We talk about von Neumann computing as the paradigm of sequential digital processing, right? And it's so unfair because actually John von Neumann, he at the end of his life, he was thinking deeply about connections between how does the brain compute versus how does the computer compute, and contrasting the precise sequential nature of a digital engine that is the computation in this von Neumann computers versus then how the brain does this massively parallel processing with extremely noisy, very efficient, but very noisy and slow elements, right, of the neurons and the synapses. And so yet our brains can achieve great feats of efficacy, in addition to efficiency, owing to the fact that you can get around the precision at the device level, at the system level, through this massive parallelism, the redundancy in representations, and as well as adaptation everywhere that gives a great performance in natural intelligence. In fact, I would say there's a precursor to many of today's AI, realizing how this is being done. Of course, John von Neumann himself could not actually do it, but then we had, interestingly, so at Caltech, so in the 80s, right, there was this great work by Richard Feynman, well known for his telling us that there's lots of room at the bottom, and he has been doing great advances in quantum physics, including also quantum computation to some extent. Carl Ramid also drove this nanoscale system revolution by realizing you can actually build circuits, and at the system level, you can take these devices and turn them into systems that can do amazing digital compute systems, right? In fact, it's Carl Ramid who actually coined the term Moore's law, as right. Gordon Moore was the one of the founders of Intel, and well known for this prediction that there was this factor 2 well, so you have every 2 years you get a doubling, right, of the density of integrated circuits, and that density doubling just over decades. This gave rise. I still remember when we're doing at Caltech, right? So we're doing this integrated circuits. We're doing things at micron scale. So if you 2 micron or 3 micron was a feature size of the transistors that we're doing. Today we're at nanometers, right? So a few nanometers. So there has been a factor of 1,000 increase in the linear dimensions of density. So then area-wise, it becomes a million. So we have had a million factor improvements. You can have now a million times more transistors that can put per square millimeter that we could say in the 80s and the 90s. And with that scaling came great advances. So Carver actually realized, in fact, much of the scaling as it was predicted by Carver, in showing that the scaling became almost as a free lunch. So everything got better. Denser scaling gave you many more transistors. You can have much more stuff per silicon, right? It gets less costly. But they also they take less energy for the compute because the capacitances are smaller, so there's less energy that's consumed in the process. And they're also faster. So it gets faster, less energy, and can do more on one chip. So everything seemed to be better. And for many years, that's been great. So Moore's law has been going almost relentlessly, but of course now is getting to that end. Both Dick Feynman and Carver, and also John Hopfield, were realizing that, hey, there are different ways of doing computation than this digital framework is telling us to do. And it's looking at different physical principles, physics of computation. So they taught this course on the physics of computing, and there they realized there is, you can take it. So Dick Feynman was focusing mostly on quantum physics. John Hopfield was focusing on the spin glass models of this thermodynamic models of computation that models say this combinatorial optimization that can be efficiently done in these physical networks that are inspired by how the brain is connected with synapses. And then Carver was taking the inspiration from biology in moving into different ways of doing silicon. And so Misha Mahowald was this very bright biology undergraduate student taking that course, and she told Carver, "This was a great course, but I didn't get much from all. This was way above my head, all this stuff about this physics." But one thing that struck me is that, why can't we actually build systems in silicon that work like the brain and that are actually take that inspiration to the extreme? So, right, this is the analysis by synthesis approach. Richard Feynman is telling us, what I cannot create, I do not understand. So if you want to understand how the brain works, you need to put it together from ground up. And Carver, and so Misha challenged Carver, and Carver, so they started this field of neuromorphic engineering, and has been a great journey. Misha, unfortunately, is no longer with us today, but she has been doing great advances, and she has been pioneering this field. Others, we have Toby, Sichi, many of the neuromorphic, I guess the field is many of us were so lucky to be at the time and starting that field. So it was quite amazing. And I highly recommend to, there's a nice, literally a nice workshop that we had now a year ago, and there we had Carver. He received the Misha Mahowald Prize, and very fittingly, and he gave a perspective of what the field has been over the last 30 years and where it's going. And I highly recommend to go. It's all recorded. You can find the video over there. In fact, it's been so nice that Shantanu, when we created this work group here, this NIC work group. Actually, it's called MySir, right?
We ran out of acronyms. I think that was
yes.
the same.
But yeah, yes, we can do great, nicer things here. Good. So what is this about? So this, what are those physical foundations that can play out here? So if you look at how the brain is organized, there's different level of scale, right? All the way from at the bottom, you have all the molecular scale, right? Where you have ions moving through ion channels, you have synapses, and then you have networks, and then you have the whole brain, right? And so it turns out that each level of scale, there are physical analogies between how, right, how the computation is taking place at that level in biology versus what can be done in silicon. And now you say, wait a minute, silicon is totally different. It's hard. You have electrons that move there. And wetware, actually, our brains are made out of gooey stuff. It's all wet. And it's ions that move through mostly water. And you have membranes that right? So this, so at each level of scale, you have this isomorphisms. So at the higher levels of scale, there's this Boltzmann. In fact, Boltzmann machines were also invented about 30 some years ago. And those were extensions of John Hopfield's, right, models of spin glass systems that are inspired by, I guess, more stochastic or thermodynamic ways of thinking about how computation is being performed in the brain. And so yeah, these physical models actually have prevailed in much of AI, machine learning. In fact, Geoff Hinton and Terry came up with this Boltzmann machines. And Geoff Hinton is also one of the Nobelists, along with John Hopfield, being realized, right? So being recognized for major contributions in the field of AI by physics, physical foundations. So physics has become the forefront, even in what traditionally would be thought to be computer science. But yeah, so even at this global level of scale here, right? So there is this isomorphism, in this case, between how electrons move through channels of transistors. So here you have I realize many of you don't have the background in integrated circuits, but so there'll be some more tutorials on this topic. But basically, the bread and butter of everything we do is transistors in this silicon integrated circuit technologies, in this silicon CMOS integrated circuit. So CMOS stands for complementary metal oxide semiconductor, right? And this is all about this MOSFET. So those metal oxide semiconductor field effect transistors. Those are transistors basically allow current to flow from source to drain. Electrons can go from source to drain, activated or driven by the gate. The voltage in the gate, right? The field caused by the voltage in the gate, the field in a channel, right? So basically, there's this, you have a capacitor between the gate and the channel. And so that field will attract or repel electrons, right? Or holes, depending on the configuration here, right? In a channel. And so this is how transport takes place, right? You have this, so a transistor is just an element that has, right? You can have a gate, you can just, the controls, the flow, right? Of the conductance of a channel. Now, on the right is a biological channel, right? Similar there, you have also, in this case, source and drain. Think of, you have the inside and the outside of your cell, right? Separated by membrane. And then, right, you have these ion channels where ion will move through those channels, that is then controlled by voltage, again, think of it, right? So there's a direct analogy between those two. And in fact, if you look at the conductance as a function of voltage, right, for those biological channels, compare them for this silicon transistor, right? Say you change the gate voltage and you measure the conductance between the source and the drain, you get almost exactly the same curve, right? So you get exponential dependence on voltage. Now, let's think of this. You have a conductance, right? And conductance is basically governed by how many electrons do you have in a channel, right? So what process would give you a density of carriers, right? As a function of voltage, or voltage, after all, is energy, right? So you have a density that is exponential in energy. that rings a bell, right? So what is that? So what would that fundamental physics be?
Can you maybe repeat the question now?
Yeah, so you have a density, right? You have a so in a channel, right? You're attracting electrons or holes, right? In the channel, right? And so you get exponentially more holes or electrons, right? The carriers in the channel, based on the voltage you apply on the gate, which means based on the energy that you give those carriers, right? So it seems like how many states you have in the system, right, is exponentially dependent on energy. There's a fundamental thermodynamic process, right? Right? So what distribution would that be? Exactly. Yes. So you have this. So where it is here, right?
E to the power of k
Exactly, right?
by t.
Yes. So n, the number of states, right, is proportional to an exponent, right, of energy with a minus sign over kT, right? And kT is your thermal energy, the same kT that we talked about, right? The same, in fact, all noise process, right? So this is basically your thermal energy, right? So that's the energy that you give your electrons or holes. And this is what it's basically saying is that at very low temperature, you get even a more crisp dependence, but at higher temperature it is more of a elongated distribution, right? And the tail gets wider the higher temperature that you have. This is just a noise process, right? In fact, this you can derive this distribution purely from a balance between drift and diffusion. So any process, right, where you have electrons or holes or ions that just move randomly, right, due to the thermal process, right, that you can that this distribution will arise naturally of this interaction or the balance that you have between this diffusion, this random walk process, versus a drift, the fact that there's an electric field that governs where things are flowing, right? And so, of course, the electric field is voltage, right? So E is going to be electric field is voltage times charge, right? So fine, there's a voltage here, and you put, say that rather than putting the charge here, let's put it here, right? So you have voltage over kT over Q, and kT over Q is a thermal voltage, right? That's a very important. And so if you work it out, K, right, Boltzmann constant, T is about room temperature, Q is the charge of an electron or a hole or anything. But in fact, just the ions, sodium and potassium have the same valence, right? It's one, right? So this is about 25 millivolts or 26 millivolts, depending it's body temperature or at room temperature, right? So 26 millivolts, right? So yes, you get exponential, and so this conductance that you have in the channels, right, would be exponential depending on this exponent. But look at the slope here. So the slope here would be, right? So you get an E fold for every 25 millivolts if it were this. Apparently, biology managed to get a much steeper slope, which means much less voltage for each E fold. In this case, 4 millivolts or 5 millivolts right on 25 millivolts. So how would biology figure to get and steeper basically means a greater separation between states, right? Between on and off, because, right? So you only have 100 millivolts available in biology, right? So 100 millivolts, right, will give you an on-off ratio. There'll be like several, 5 or 6 orders of magnitude, right? If you do this measurement in silicon, right, the slope is actually, so you get actually 25 millivolts per decade per E-fold, which means you need to have 5 times more voltage to have the same contrast, right? The same, right? Basically means in silicon you need to basically your power supply needs to be at least 500 millivolts, not just the 100 millivolts of the typical sodium versus potassium difference, or reverse potential that you have in biology. So actually 5 times more voltage. Right, so you can't go much below half a volt in your integrated circuits, because if you're going to blow that, you can't turn anything off or up, right? Yes.
Could you play with temperature and get things a little bit closer?
Oh, sure, yes, but that's kind of cheating. So yes, we can, we'll just cool it down. And actually, that's what quantum computing does, by the way, right? So quantum computing is great at 0.1 Kelvin, but so with neuromorphic circuits, we can cool everything. So yes, anything that quantum computing does, we can do as neuromorphic engineers too. If we get the same temperature, if we can cool things down to 0.1 Kelvin, we'll actually outperform any quantum computing system that exists today. But yes.
Is there a relation to the V threshold of the transistor? There's like
No, it's not.
0.5.
It's not. It's the threshold will just change the offset, right? The threshold will move things left and right.
Yeah.
But right, so on the log scale, the slope is what matters, right? So, but yes, what will be another? So let's look at this again, right? So here, what is this thermal voltage, or this, right? What gives the slope? It's KT over Q. K we can't change. P, yeah, you can change, but that's kind of cheating, right? But what else can you change here? What is Q? Is the valence, right? The valence, right? Now, what did biology do? What's the valence for sodium and potassium? So now in biology, there's actually, those channels are actually sodium or potassium channels, right? You have different reverse potential that gives the rise to the battery, right? The change, right? So, but that's still a valence of 1. So now there's actually another. So what would happen in ion channels? So what's an ion channel? So you have this sodium or potassium that goes through this pore, right? This ion channel. Now, what is it suggesting? What this dependence suggest? Somehow the effective valence is not 1, but it's more like 5. How did biology manage to do that? So what did
leave this room until everybody gets this? Considering this is the inspiration for all of neuromorphic engineering. Yeah, this room, everybody.
So in fact, you've heard about Hodge and Huxley, right? Hodge and Huxley is those are two again Nobel laureates that did the pioneering work on understanding the basis for how neurons actually operate, right? And yes, you have sodium and potassium; those are important ion channels that are active, right? And their opening and closing governed by the voltage across the membrane governs, right, the spike.
Who knows the answer and doesn't want to give away the answer? Who knows the answer?
I'm not sure if I
Raise your hand, legit, you know the answer, but now you know the answer, right?
I know the answer, I forgot it.
Come on, this is the foundation.
Yes.
I remember like there's 2 calcium, 3 sodium transfer.
You know, well, this is there's so many other things that go on in the model of Cawenberghs.
Give them a clue, point at something on the slide.
Yes.
What's the critical thing that you have to think about?
Yes. So what is happening here? So you have this pore, right? So how does the ion make it through it? Does it? In fact, what is right? So all of Hodge and Huxley is actually you get an electrical circuit, and electrical engineers can totally understand everything in Hodge and Huxley is a very simple circuit, right? You have this, but there's one phenomenological thing there. What are the ion channels doing? And that's so how does
Where's the ion channel? Can you point to it again? Yeah, that one.
yeah
The structure there, that's a structure, right?
the structure. So what is it? It's actually protein. It's a protein, and right, and it folds and folds, right, based on voltage. So when more voltage is across the membrane, there'll be a change in the configuration of the protein, which would change the way that ions can make it through.
How can you make that protein feel the electric field more strongly? How can you do it?
More ions.
More ions or what? The protein is built out of atoms, which some might have charge. So what?
So created a potential difference, larger potential difference by?
No, it's the same potential across the membranes. So what do you do to the ion, to this channel, protein? This protein made out of hundreds of thousands of atoms. How can you make it feel the charge more strongly? Feel the voltage more strongly? What? Yeah, how do you polarize it? It's polarized by the field, right?
Unstable?
Yeah. More unstable, but how does that protein feel the electric field? How does it feel it?
Because it's gonna bind.
It has that charge in it, right?
There's additional mechanisms to it that touches like there's a power supply. ATP power supply. No?
Provide the energy for that.
Okay, this is. So,
It's a remote comment.
Oh, is it like a capacitor with the thickness?
well, it looks like the comments on the chat have diverged into nuclear fusion or things. So the power grid is a different thing. But then again, so there's something called correlated transport. Is that not a single ion make it through, but they need to go right. They need to work together, right? And so somehow biology figured out that hey, even though because noise-wise, outside of the channel, ions will just move by themselves. But going through the ion channel, they need to go together, not a single, right? So not a single, and that's why you have less gates. So you have this the gating variables in Hudson-Huxley that all work together. There are probably different ways of it.
I don't think. In this complex protein, which is this channel, you can go into it again.
Yes.
There's charges.
Yep.
There's multiple charges, not just one charge, the electric field on, there's like 4 or 5 charges.
Yes.
And so the structure can feel more force from the electric fields because there's more than one charge there. Put 4 charges there. Along that chain, the long chain that's folded up, there's 4 or 5 charges that the electric field can act on.
Yeah.
They all act together on this protein. You understand now? Now the same electric field creates more force.
Yeah.
Yeah, so
There's another sort of the standard mathematical model for it. You view that as there's some number of particles in that channel.
Yes.
doesn't matter what's in the channel.
No, that is important because after all, it's
Protein
thermodynamics.
doesn't matter what's in it.
No, but you add and then you remove from the other end.
Yes,
So-
exactly.
And then there's a population in there, and that's what amplifies.
Exactly. So no ion can go out unless another ion comes in. So they go together.
I think the protein itself is charged.
Sure, of course. Yeah, of course, yes.
No, because otherwise you wouldn't have to. Yes.
Because after all, what is again? So where does it come from? This is about drift and diffusion, right? It's the way in which ions move, and now they need to move together, which means the effective valence or the effective charge, what goes to the channel is actually 5 times larger than in any case.
How it is different in silicon, because you have the
Silicon, well,
electrons going as well in
yes, but
So
there's
you can
no
find a transistor that does this trick.
yes.
Can make $1 billion.
And yeah, there are advances in different conferences, there are different meetings, right, on electron devices, where they figured out ways of doing the same correlated transport, ensuring that when electrons move across, that other electrons must move together, because again, the space charge thing, a single electron can't make it, another electron needs to go along with it. And this way they can get steeper slopes. But in any case, this gets deep into physics.
Is it the 3 sodium ions and 3 potassium ions? Like there's a 5 atom?
Well, strictly speaking, if you look at the Hudson-Huxley model, right, what is it? You have m to the 3rd power times h. Those are m and h gain variables for sodium. And then for potassium, it's n to the 4th, right? So 4 is different from 5, but it's close, yeah.
Yeah, so you have to understand, if you're not from this background, you have to understand the observation of these 2 curves here. And the fact that the current through a transistor is exponential with voltage, and also the conductance, not the current, the conductance across the membrane is exponential with the voltage. Understand? In one case, the current is exponential. In the other case, the conductance. That's the thing that inspired Carver as a device physicist, of a background and training and discipline to start the whole field of neuromorphic electronics.
Okay,
That
good.
single observation.
Okay, so I have a few minutes left. So let me, so the important, but actually this is important, so that we can design circuits where transistors, rather than being just an on-off switch for digital compute, they're actually analog, very rich analog devices that give you orders of magnitude dynamic range, right? That's a change in the gate voltage, just over a few hundred millivolts, right? You get orders of magnitude change in conductance, and so this is called the sub-threshold region of the MOS transistor, by the way. So that it'll be above threshold over here. That's where most circuit designers operated, at least in the last 30, 40 years. And so Neuromorphic engineers like to operate in this sub-threshold regime, right, where you get this currents from femtoamps to nanoamps, as opposed to microamps and to milliamps. And you get much greater dynamic range, much greater gain, because the slope is steeper, right? So everything gets better. And if it even scales nicely, because you can make a circuit that if you increase, let's say if you give it 10 times more current, it gets 10 times faster, right? So you get a bandwidth and power trade-off with this direct, which means you can design an efficient circuit at almost any frequency range, and it will give you the same efficiency. So that's the bottom line. I just want to highlight a few, because, and this is more a tutorial anyway, right? So then Misha and Carver took this inspiration from how the retina is organized, right? And again, where does the light come in, by the way, in the retina? So you have on top here, you have your cones and your rods, the actual photosensitive cells. And then you have this layer, you have the horizontal cells and the bipolar cells right underneath. Light actually comes from the bottom here, right? It goes through all those cells and eventually reaches the rods and cones up here. And so I can take that structure and actually build the silicon retina, right? With basically, in this case, you compact the entire 3D structure or this 2.5D structure into the 2D technology in silicon. These days, you can actually go 2.5D2, where you can actually have different dyes stacked, right? You can do multiple layers. But at least initially, 30 years ago, this is what we did. And so there's a beautiful Scientific American article that I recommend you to read. This was the concept. So you have this horizontal cells implemented with this network of conductances, lateral conductances. And then you have this the receptors, and also the vertical, because for the cells, like the bipolar cells, implemented in each pixel. So now you have physically a circuit, right? Where you have photosensitive elements. In fact, we have those bipolar transistors or this parasitic bipolars or photodiodes native in this process that can give you currents proportional to how much light comes in. And then you have all this sub-threshold analog circuits that can do, say, what your bipolar and your horizontal cells are doing. In this case, you would take this difference, right? You have this, you have a follower here that takes the log encoded, the logarithmic encoded, again, the same log encoding that you have in sub-threshold, right? So you can go from a current to a voltage in a log fashion, right? So the gate voltage is logarithmic here in current. And so you have this log encoded intensity. And then you have this network by which you laterally diffuse your activity, and then basically construct an average, a spatial average of this log encoded intensity voltages. And then you take the difference, right? And so that gives you a contrast enhancement. So you can get an output in each pixel is proportional to the contrast of its log encoded intensity against the average of its neighborhood, right? And that's basically the model here of silicon retina, the first one, right? And so just the same technology, again, CMOS does everything, right? Those photoreceptors are actually natively supported in the process. And so now this comes out. This is what you get, the output of this imager. In fact, this was Misha's cat, and she spent a day trying to take that picture, herding the cat here. There's a lot of fixed pattern noise, and actually we can get around that with, so the field has evolved since then, but at least, right, so there have been advances in circuits that actually give an event-driven output. And you have heard of event-driven representations, right? Where you model not only this horizontal cells, bipolar cells, but also American cells, and then eventually the ganglion cells. The ganglion cells are the ones that actually are spiking, and they give this spike-based representation of this visual encoded scene, both spatial and temporal contrast encoded activity over the optic nerve to the rest of the brain, right? And so that's an example of those silicon retinas, right? So you have this sensor, you have an analog input from the real world, and then the output of this chip are events. Those are spikes. Those are asynchronous events that come out, right? Modeling basically the ganglion cells. And that framework has been driving much of neuromorphic sensing and computing, where you get this event-driven representations. And so the latest silicon-based or silicon retinas, right, are actually dynamic vision sensors that focus on this temporal contrast enhancement. And that can be done very efficiently, even with a few more transistors beside what is called an active pixel sensor. In fact, that's what's work with Raf at Cummings, Udian Malik, Mike Chi, right, of this event-driven representations, where you can get this very efficient contrast enhanced, temporal contrast enhanced output. And now there's some, so Raj, right, and I developed, so there has been a whole generation of dynamic vision sensors. But there's query-driven dynamic vision sensors now that extend this framework that give us a really great efficiency down to 6 picojoules of event. And so there's now a work group that is extending that frame, this design of APS inspired or APS / dynamic vision sensor inspired silicon retinas combined with asynchronous digital logic for encoding. So that's, I think I'll just highlight here so that's sensing, and for compute, the method, right? So, for computation, basically now we can use these event-based representations from sensors and couple that to circuits that can implement cortical representations, like modeling the compute, massively parallel compute, the synaptic connectivity and plasticity, right? And this is done in this event-driven framework in the address domain, so that rather than making circuits where you actually wire every axon and implement every synapse, or hardwire them in silicon, which is impossible. We use this virtual framework for virtual synapses, virtual connectivity with a digital memory that can be dynamically configured and for implementing reconfigurable connectivity and plasticity, right, in large systems. I'll probably stop here, but so we can get this so neuromorphic computing. So at the beginning of the talk, I contrasted the old school AI with the new school AI, which actually really, I would say, neuromorphic computing. And so this is shown here in this contrasting the task complexity. So Go would be really complex up here. Chess would be, say, here. Very simple. Tic-tac-toe will probably appear. So on the log scale of task complexity, right? You get a very compressed scale and log scale, and for many years AI has not been able to get anywhere at a reasonable. And by the way, we say complex task. For us, it is difficult, say, to do our taxes or so. We wouldn't trust, say, a neuromorphic chip and to do a spreadsheet. Leave this very simple task. Leave that to a digital computer. But just navigation, right? That's a very hard task for computers, for traditional digital computers, and that's where neuromorphic or analog models shine, right? So this, so in terms of the machine complexity versus task complexity, there is a favorable trade-off, in fact, called out rather than the curse of dimensionality, called out the blessing of hyperdimensionality, right? So that the higher dimensions you live in for doing pattern recognition, the greater advances that you have in the greater compression that you have due to this collective analog framework that gives you much more favorable scaling of machine versus task complexity, right? And so you can contrast now this. So the contributions by the neuromorphic community are then to minimize this energy as energy per operation times operations per task. And so neuromorphic computing can lower that energy per operation by building circuits with computing memory circuits, right? Where you can then minimize the femtojoules per specific operations, right? So by bringing the memory, the compute closer to the memory. And then we can work hand in hand with the neuroscientists, cognitive scientists, and machine learning, I guess, experts for lowering operations per task. And those have to come together, and that's how we are able to. In the workshop here has been progressing over many years. Neuromorphic engineering has been operating in this unfavorable regime. So now finally we can go at a large scale, building systems that have millions of neurons, billions of synapses, operating at really great efficiencies, and working alongside with cognitive science / AI / computer scientists for them actually getting at this lower representation through deep learning. Right? And I think I'll stop. So that's basically where we are in the field. And I think that's where we should further move forward to. I think I'll stop here.
Thank you. I think there was a discussion thread that started online. We don't have to go into too much detail, but I think there's some agreement. I think that maybe the neuromorphic field, like the claim of things getting better because they're more energy efficient, so we will use less power, is maybe not historically, at least, not the most likely outcome. So the question is more like, will things get using the same amount of energy? Will things get better? And so maybe it might be an interesting question, like what are the things that neuromorphic hardware can do or enable or something that are just hard to do right now, rather than just trying to make the case that we do the same thing but cheaper.
Yeah, that's basically what I meant to emphasize here, right? So clearly there are certain tasks that you don't want to give to a CPU, right, or even GPU. The very hard. Actually, I'll take it back because the world seems to be taken over by GPUs or general purpose graphical processing units, GPUs. They're actually notoriously, well, the history of that is GPUs were great gaming devices. And at some point people realized, hey, those convolutional operations that are being done for graphics rendering in those for gaming applications can also benefit AI, or in this case, neuromorphic, I guess, neural application, right? Where you do a lot of convolutional processing, just the same way that you do convolutional processing in the visual system. And that's why GPUs really took off. When they're general programmable, that's great. But in a way, the latest GPU processor is actually, I would say, almost neuromorphic. And it's interesting because Bill Daly, one of the founders or one of the lead architects in systems, about 10 years ago, they came up with this efficient inference engine, right? And so, and the claim, the great efficiency claim there was, hey, when you do all this vector matrix operations, don't multiply by zeros, right? So if you have a lot of zeros in your matrix, skip those zeros when you multiply. If you have a lot of zeros in your vectors, skip those zeros, right? Isn't that exactly what neuromorphic computing does, right? So you take advantage of sparsity both temporal and spatial sparsity. And yeah, so that event-based representations are efficient. Event-based representations as well as hierarchical structured networks are efficient for, can be efficiently implemented with neuromorphic hardware. And so many of those GPU-based systems today are actually a digital extension of what we're doing. So in some way, the smart AI chips today are not too different from the smart neuromorphic chips that we're building. But still, there'll be some room for general purpose von Neumann slash computing, and those two have to go hand in hand.
Gert, are you taking questions from online?
Yes, absolutely, Grace. Yeah, please. Yeah.
So I really like this chart where you show the machine complexity versus task complexity, and how that because of the scaling in recent times, Neuromorph is able to operate in this beneficial gray regime. What's kind of not clear to me is, what does Neuromorphic today need from modern neuroscience findings?
Oh, yes. So very good question. So I started off with the inspiration and I think that Carver. So it's interesting because there's certain, for instance, the event-based representation, is that really, have you learned really from biology in building those efficient implementations, say, of how we communicate? So there's a lot of there's knowledge gained, right, from neuroscience today that translate in so going back to the entire field of AI today is really, in a way, it's very much driven by understanding of how you have layered structures in the brain, say for cortical representations, reinforcement learning, right, basal ganglia. And another important domain here, for instance, understanding how hippocampus works, and that's something that is not yet fully implemented in the neuromorphic systems. Can we understand efficient place coding, SLAM, right, for navigation systems, but also understand, say, the transfer from short-term to long-term memory, and that has not been efficiently implemented yet. But inspiration from neuroscience can help develop new, and in fact, I have some slides going over, just highlighting, right? So we can have those mammistive networks, right, where we can not only implement this long-term plasticity of what is happening with the synapses, right? But also have this hippocampal network, because hippocampus driving the plasticity, and having both long-term endurance, while also and ensuring being able to do fast, I guess, single-shot learning. So the plasticity dilemma, right? So transfer from short-term to long-term memory is something that we can.
Thank you. That's helpful.
And dendrites, of course, yes. Thank you. Yes, I should learn from Johannes. And Johannes has been pounding in my head saying, yeah, we want to have dendritic computation. Of course, yes, we're actually doing, so you can implement this dendritic computation in the analog domain, right, in this IFAT circuits. Absolutely. So dendritic computation is extremely important too. Yeah. And in fact, Johannes, you had a workshop where you attended, where there's a lot of synergy between neuroscience and computation.
There's a workshop on dendritic computing, which is mostly neuroscience, but there's a lot of people there that are interested also in neuromorphic engineering. So there's sort of a link there, at least in that sub community, I would say. Yeah. But I think it's still pretty early on. So let's see. But yeah,
is that Yota's meeting?
Sorry?
Are you referring to Yota's meeting?
But the Gordon's research conference in Ventura, I think, on dendrites, and there's also a different one. I think, Yota is organizing it. I think there's two alternating ones.
Yes.
Yeah.
Let me just make a plug. because Grace one of NIH is actually organizing it will be a mini symposium on this interface between neuromorphic engineering and neuroscience, and with even applications to health and biomedical systems, right? At the Neural Engineering Conference, which will be held in San Diego, November 11th to November 14th, just before the Society for Neuroscience meeting. There'll be really great things happening, by the way, at that conference, and we highly recommend you to participate. In fact, there's still a call for, there'll be another call for abstracts and papers.
Maybe we should put that on the WhatsApp.
Yeah, I'll do that now.
But also, so we are now like 3 minutes into the coffee
Yep.
break. I think
Yes.
there is a talk or tutorial, I think LNT tutorial. I'm not sure if someone from the LNT group knows if this is happening here or in the LNT room. Does anyone here know?
It'll be here.
I'll be
Will
here.
be here? Okay, so yeah, now we have a coffee break. So then whoever's interested, be back here in 15 minutes. And yeah, thanks for the talk again.
Thank you.
This is the LT tutorial. That's an introduction to vector symbolic algebras, or VSAs. I'm going to start from just the very basics and then describe how these methods apply to computational neuroscience and AI briefly at the end. All right, first, what is a VSA that we keep talking about over the last couple of days? So vector symbolic algebras, or VSAs, they're also known as vector symbolic architectures, and sometimes the phrase hyperdimensional computing is used synonymously, are meant to sort of bridge the gap between symbolic approaches to cognitive science and good old-fashioned AI, and more modern connectionist neural network approaches. Draw insights from various fields. From neuroscience, drawn inspiration from the high-dimensional, highly distributed representations in cortical areas, and from cognitive science, drawn inspiration from the manner in which language and thought incorporate symbolic reasoning and compositionality. And what they actually are in practice is that we have high-dimensional vectors that are used to represent concepts or symbols. And if you have like a full, end-to-end system, a large, brain model or robotic system, you think of these vectors as coming from various perceptual systems. In practice, if you have a more isolated system, these vectors may be learned, engineered via some heuristics, or sometimes they can just be set randomly, and that works. Ideally, though, if they're set in a more intelligent way, there is a similarity measure in the vector space, which serves as a proxy for the semantic similarity of the underlying concepts. And this on its own is not very unique, in AI. There's high-dimensional feature embeddings are used all the time, in which there are distance measures in those spaces that carry meaningful semantic content. But what makes VSAs unique is that they also define this explicit set of mathematical operations in the vectors, which combine these vectors and manipulate them. So there's an explicit language for compositionality in VSAs. There are two main operations that are defined in a VSA. First, there's a bundling or superposition operation. And this is a way of representing multiple objects together, representing sets. So you combine vectors to get a single vector that is similar to all of its component parts. Sort of an OR operation. And there's also a binding operation, which is another way of combining vectors to create novel concepts, though. So a new vector that is dissimilar from all of its component parts. And binding is also often used in constructing slot filler representations. So an example of this, maybe we have this simple object with some different properties, and we represent it by taking the color vector and binding it with the red vector, and then bundling that with the type vector bound with the door vector, et cetera, et cetera. This is an example of a slot filler representation, in that the vectors for color and type are slots. They define roles, and what they're bound with are fillers. They are the values of said roles.
What's the difference between this binding and bundling again? Binding is equivalent mathematically to.
It's like an kind of like maybe or versus and in some respects, but maybe one way to think of it is bundling, you get something that's similar to all the things that went into it. Binding, you get something dissimilar to all the things that went into it. So,
Why
you know,
dissimilar?
yeah, so
But why is that called binding then?
binding, it's a way of sort of, yeah, associating things together that is a novel concept in and of itself. So something that is red in color is distinct from the concept of color in general. And having these multiple operations for compositionality is quite useful. If you just had bundling, you could not easily extract all the things, get all the things that went into it necessarily. Whereas when you have this binding bundling structure of a slot fill representation, you can extract the information that went into it approximately using an unbinding or inverse operation. So this is a way of undoing the effect of binding. In some VSAs, this is exact. In some VSAs, it's more approximate. But you could use this with this vector, for example, by unbinding the color vector to get something that's approximately the red vector. So you can create these compressed structures.
It's equivalent to dotting it. I mean, just so I understand, that's equivalent to if you want to unbind the red, you basically dot your vector with the red vector. You dot it together and that leads you only something pointing in the red direction? Not like that. It's not that.
It's not like that. It's not the similarity measure, but it's there is an operation that, yeah, like that, you apply it and you get something that's like the red vector, but with maybe some noise as well.
Can I try to make a computer science analogy and then
Yeah.
we can see how far we can stretch it?
Yeah.
So to me, it seems a bit like, so the binding is a bit like a tuple. Like you have two different things.
Yeah.
You're putting them together. The first position in the tuple and the second position in the tuple, they have different meanings.
Yeah.
And the two are now one thing, right?
Yeah.
And bundling is a set. Like you can put a lot of tuples in a set. And you have a set of tuples, but sets and tuples are different things.
Yeah.
Right? That kind of, does that make sense?
That definitely makes sense, and that's, I think, actually a perfect way to explain it. Though I guess with tuples, sometimes the order matters. With binding, whether or not the order matters depends on the details of your VSA that you've used in practice. It may be commutative sometimes, practice. But you can create these structures as these single compressed vectors and store them in memory, then later retrieve them and use these operations again to manipulate them, add new information, or query for information after the fact. And you can, use more of these operations to do more complex representations. You can represent, objects with different properties in images. You can represent images in bounding boxes. You can represent ordered sequences. Or you can even represent graphs. If you have an undirected graph, you can represent, you can bind the head tail node with the relationship as a triplet and then bundle all of the, all of the connections in your graph. If you have a directed graph, you could use maybe something like a slot fill representation where you have a head, tail, and relationship slots that you then bind with the fillers and bundle all of the connections in the graph. All right, so why are we talking about VSAs at the Neuromorphic conference? There's a deep history of connection between VSAs and neuromorphic computing. The whole idea about VSAs originally was a way to take these traditional models from cognitive science that involved symbols that were manipulated and reasoned about in the models to model types of cognition and translate that into neural networks. Because now our symbols, rather than being these abstract things, are vectors that can be encoded in a neural population, either directly or via some population code. And rather than having these explicit symbolic operations, instead we have these vector operations, which are generally defined to be quite amendable to implementation in neural networks. And so the neural network can have transformations that are performing these operations to construct representations and reason about representations. And thus, a reasoning system defined in this way can be implemented on neuromorphic hardware. There's a very nice paper about this vector symbolic architectures as computing framework for emergent hardware that I recommend as an introductory read that has also a lot of good examples about types of VSA structures you can create. And they sort of posit VSAs as like a programming language for neuromorphic hardware, a way of defining algorithms to compute various functions that can then be very easily translated into these approaches. Obviously, VSAs that use binary vectors are particularly suitable to neuromorphic implementation, but even if you have real valued vectors or something more complex, there are various methods like the semantic pointer architecture and software packages like Mango-SPA that have methods for population codes that allow you to represent these vectors in your spiking neural networks. And this software package also has pre-built-in networks for doing the bind-in operations and all the operations you'd want to do. Other useful package, computing resources is this Torch HD package, which has a whole lot of functionality for a particular type of VSA. In fact, the one that I'll be talking about today. Yes?
Maybe you said this earlier, but when you change from symbolic to a representation like this, does that change the decision boundaries?
Decision boundaries?
So
it does.
Symbolic, it's very clear the decision boundaries, but
it introduces fuzziness. It does, because
is that good?
You can use it, and we're going to talk about some ways it's useful. There could, I mean, if you really, there's ways it could introduce noise and approximation errors. You know, when I have these different data structures, I maybe almost made it sound like you could have any complex super hierarchical data structure, but the truth is that depending on the dimensionality of your vectors and the complexity of the data structure, you can encode it in these vector representations, but it may be a lossy encoding that may introduce some noise and approximation.
Which might be okay.
Yeah, you know, that could be a feature, not a bug. So as you maybe picked up with me talking about, like, depending on the VSA and real versus binary, there are many VSAs. VSA is just sort of a family of fairly generic methods. There's, for example, holographic reduced representations that were invented by Tony Plate in the 90s. And in this VSA, your vectors are real valued. They're generally actually from a subspace of the real space. Bundling is just element-wise vector addition, very simple. Binding is circular convolution between vectors, which is just element-wise multiplication in the Fourier domain. And your similarity is cosine similarity, our favorite similarity measure. There's also Fourier holographic reduced representations, which is very similar, but it's in the Fourier domain. So your complex valued vectors and the bind-in, you just do that element-wise multiplication. There's also other VSAs that define the vectors over, have binary vectors or have bipolar vectors like plus and minus 1, or have integer valued vectors, and that use different bind-in and bundling operations that have different degrees of complexity. In this talk, I'm going to focus on holographic reduced representations because it's quite nice to represent numbers in this system. But Fourier holographic reduced representations are very similar, so a lot of what I'm saying translates quite easily to working in that space. All right, so I mentioned numbers. So, I talked about having these discrete symbols and data structures like graphs of discrete symbols, but maybe you have data structures that feature numerical values that you want to encode and represent. One way you can do that is using this binding operator, basically doing iterative self-binding. To represent an integer, take some base vector. Here I have that noted with a bold 5 that represents sort of 1 of some value of interest. And if you bind it itself n times, that's now your high dimensional representation of the integer n. And the nice thing about this is now binding these representations together is equivalent to addition, and you can do iterative binding and unbinding to count up and down. Now, this space vector, it can't just be anything. If you set it sort of arbitrarily, you could get situations where you do this iterative self-binding, the magnitude of your resultant vector can grow and shrink without bound, which can be problematic when you're representing spherical populations and undesirable for various reasons. So it's nice to have particular constraints on this. Namely, this vector should be what we call unitary. This is the way the vectors are generally randomly generated in Fourier holographic reduced representations. What I mean by unitary is just that in the Fourier domain, the vector, all of its components are unit modulus. So, the Fourier domain's components are complex numbers, which you can write as, r times e to the I theta, some vector in the complex plane. And unit modulus means that like for that vector, the r is 1. So each of its components in the Fourier domain are only defined by an angle, a phase, which I have written here as this bolded phi vector. So when I have an e to the power of a vector, that means element-wise throughout this presentation. You still have freedom to choose that theta vector as however you'd like. Well, with some constraints, it does, if you want to go back in the real domain, holographic reduced representations, it needs to have conjugate symmetry and some other notes, some other constraints. But for the most part, it has a set of unique terms that you can explicitly set, or you can sample from some distribution, like a uniform distribution, as I've written here, or a normal distribution. All right, are there any questions at this point? Cool. All right. So the nice thing about this is this generalizes quite nicely to representing real valued numbers. Binding is the same thing as element-wise multiplication of the Fourier domain. So self-binding, n times, is the same thing as taking this vector in the Fourier domain, the e to the I theta, and raising it to the power of n element-wise. And we can just swap out our integer n with our real valued x. And yeah.
It seems incredibly inefficient. Just a few bits of the integer, and now you have to use thousands of bits to do the same thing.
But floating point is so great.
Huh?
But floating point is so great.
Yeah, even worse.
No one's laughing.
Yeah, depending on, what you want to do, like maybe there's, just stick with the integers. This is sort of nice because now you have these high dimensional vectors that you can bind with discrete concepts. And if you had a graph that has integers in it with different relationships, you can use the binding and bundling operation in this vector space to represent structures. Yeah.
Is there any relation to positional encoding?
Yeah, this is often how positions are encoded in VSAs in this style.
Increment and transformer.
Oh, and
Yeah.
transformers. Oh,
Is there any relation?
it's somewhat similar in some respects in that it's that does feature these periodic functions of
Yeah.
different frequencies.
Yes.
In the sense of being kind of similar to that in some respects. It's not
It's not exact.
yeah, it's not exact. There is, I think, work that has explored using HRRs to replace positional embeddings.
Yeah, it's the former HRR former.
Yeah. So yeah, people have made that connection before and taken it a bit further. I don't know if they did that though for the real valid ones. Let me move on to talking about that. All right, so now if we want to represent a real valued variable or some vector, it's n-dimensional, we can now use something very similar where we have some starting vector that's now e to the I capital theta. It's now a matrix. Instead of just raising to the power of some integer n, we have some vector x that we multiply by this theta. So this is maybe easiest to sort of visualize in this 2D example. You have some x in a 2D space that's sort of unbounded. It can be anywhere in the space. And you take the dot product of it with all of these different thetas that are the rows of this theta matrix. And you store the results of those in the angles of these complex exponentials, these phasors. So you go from this low dimensional vector in this unbounded space to now a larger number of terms in the complex plane, but they're highly constrained. They're all on the unit circle. This is maybe kind of similar to represented time or positions using various periodic functions with different periods.
Sorry, how is this different from just changing the basis of the space?
Changing the base space?
Yeah, in algebra, is it somewhat similar, or I'm missing something?
It's a non-linear projection into the high dimensional space. So it's not, but it's.
So does this mean if I have an n-dimensional vector x, I'll use n of these data vectors?
you ideally, you want your theta, number of thetas to be much larger than n ideally. Otherwise, it will be a poor approximation, you know? Because
Okay.
you think,
So in practice, if I have a 3D vector and I want to represent it in this way, like how many of these like basis data vectors would I have?
something on the dimensionality in the order of like hundreds,
Okay.
but sometimes you can get away with less for certain applications. In hyperdimensional computing, often they may use like vectors of like size of on the order of like thousands of dimensions, tens of thousands. That's more common with VSAs that use binary representation. So for these, usually hundreds of dimensions, it's sort of quite reasonable for most tasks.
Wait, another question.
Yeah.
What do you mean exactly with fractional binding? Was that the thing in the previous one?
Yeah, then that you're like
It's repeated
self-binding, but a fractional number of times. Yeah. Cool. So this is just some projection to a high dimensional space that's parameterized by this theta matrix. And actually the mathematical form of this projection is very similar. It's actually almost exactly the same as that of random Fourier features. I'll read that in a second. Random Fourier features, which is a popular method in machine learning for approximating kernel functions by mapping input data into a randomized high-dimensional Fourier space of some sort. And the only real difference, I think, between this stuff, these representations I call spatial semantic pointers, SSPs, they're also known as fractional power encodings, is that they exist within the broader context of a VSA, unlike random Fourier features. Did Terry have a question or? Okay. Okay.
I was just gonna make my PCA comment, but don't worry.
That's a good point. Yeah, and that sometimes projecting, it's like the kernel trick, projecting into a high dimensional space. Sometimes functions that were quite complex and nonlinear in the lower dimensional space become really, simple, can be approximated to a linear function in the high dimensional space. So that's another benefit of doing this sort of projection. Yeah, but these vectors, these SSPs exist in the broader context of VSA. So all the operations I described before can be used with these vectors. Binding of two SSPs with the same base matrix is the same thing as addition of the encoded variables. Unbinding corresponds to negation. And we combine SSPs with vectors that represent discrete concepts and symbols to represent, here a star at some location in space. It's a little toy example. And we can use bundling to represent, sets of locations or areas. And you can use binding in combination with bundling to represent, say, multiple objects of different features at different locations. The similarity measure is also very meaningful when working with SSPs. So the similarity between these SSPs induces a kernel function. And this is what that function looks like. This is the similarity between the vector representation of 0 with the representation of x over x. So you can see that this is not like a super local representation or discrete. There's some fuzziness. So values, SSPs representing values close to 0 have some similarity with the representation of 0. And that similarity drops off and then kind of becomes small, but there's some oscillations, some noise as you get further out. And the amount of the sort of degree of those oscillations, their size will depend on the dimensionality of vectors you're using. And the size, the width of this bump, you can tune with some parameters in the projection as desired. And plotted here on the left is also just a visualization of an SSP in the Fourier space, plotting like each of the phasors, its components, as these little vectors in a circle that's colored by the angle value. The exact shape of this induced kernel function will depend on your phase matrix. So you can set it to try and match some target kernel function, or if you've sampled the components of your phase matrix from some distribution, then the kernel shape will be related to the Fourier transform of that distribution. And we can plot this induced kernel function if we're representing points over 2D space with a heat map. And here I'm visualizing the components of an SSP in the Fourier space with, again, these little phasors, but now plotted as an array. So altogether, for all of these VSA operations, you can do things like represent a scene of objects, discrete objects with continuous features, say at different locations or different sizes or other continuous values, all in superposition, representing a scene or a cognitive map in a single compressed vector that then can be stored in memory in like maybe a working memory circuit or an associative memory, and that can later be recalled and queried for different object locations, and you can sort of plot the results of those queries using this similarity operation. If when looking at these, similarity plots, you thought maybe that's kind of looks like a probability distribution of some sort. I don't know if any of you thought that, but if you did, you'd be on the right track. And this is work Michael has done just a few years ago. So if we take samples from some distribution and then encode them as SSTs and bundle the result together, then the similarity of some new sample X with that bundle is proportional to the probability of that sample under the original distribution. The similarity isn't directly a probability because similarity it's not non-negative for one, and it's not normalized. But if you apply some sort of function to make it non-negative and normalize, then now you can interpret it as a probability. Like for instance, you can apply some shift and rectification, or you could do some sort of like squaring and normalization, whatever your favorite operation is. And so we can represent probability distributions with these single vectors that can also be, as I said, stored in memory and updated and used in various ways. And this is a kernel mean embedding, and this is kernel density estimation using SSPs. And this is not just limited to the continuous representations in VSAs. We can have representations of distributions over various data structures that you can define for VSA. For instance, you could have a mixed discrete continuous, a distribution defined over mixed discrete continuous values, and bind discrete symbols with the continuous values and bundle the results to represent some distribution. You could also imagine instead your samples could be representations of graphs or images, and you can define bundles over those samples. Are there any questions at this point?
The graphs, not really.
How to represent a graph, or
no, but this graph.
Oh, this graph. Yeah, so this is showing a distribution that's over two variables. One is x, which is discrete; it can take on values a, b, and c, and one is some y that can take on values from 0 to 1. And these are the dotted line is some distribution in this space. And then the bar plot is showing samples that were drawn from it. And then those samples were encoded in this way and bundled together. And then we did a transformation was done to get a probability from the similarity of said bundle. And that's plotted in the blue line.
So M is the blue line.
Yeah. Or it's a function of the similarity.
Yeah.
Can you also sample from this distribution, or what can you do with the similarity?
Yes, you can sample from the distribution. You can compute, the gradient of probability of these vectors. You can update them online. You can use them for trajectory optimization and various things. And Michael, he's done a lot of work in this, so he knows all the things you can do as well. And he's also, I think, worked on constructing some neural networks for computing various properties of a distribution when it's encoded in this way. All right, so now I want to talk about some applications of VSAs, first focusing on computational neuroscience and modeling, and this is mostly my own work. So as I said before, the kernel function you get depends on your phase matrix. If you have, and I want to talk a little bit more about the details of that now, if you have one unique row in your phase matrix, then your similarity function will look like a wave. There's examples in the notebook where you can play around and see this. and where the propagation direction of the wave will depend on that row, its direction, and the frequency of that wave will depend on the scale of that vector. And so when you have multiple unique rows in your phase matrix, the resultant kernel function, the similarity, is the interference pattern of all those waves. Which is why, so you basically, I'll have this, that's why you can approximate different kinds of kernel functions. It's like some sort of Fourier decomposition. You can also, though, set these rows of your phase matrix explicitly to get some desired, interference pattern. If you had SSPs representing a 2D variable, and you just had two unique rows in your phase matrix that were 90 degrees apart, your interference pattern would be two waves that are 90 degrees apart. It'd be a rectangular grid. If instead you had free rows that were 120 degrees apart, your interference pattern is a hexagonally gridded pattern. And this is interesting because there are neurons called grid cells in the medial frontal cortex of mammals that fire hexagonally gridded points as an animal moves through space. There's also some evidence of grid cell-like encodings being used for non-spatial continuous variables and being a more general, efficient coding scheme. So we can construct SSPs that have this similarity map. This actually isn't a really good representation in some ways, because now I can't uniquely distinguish points, right? Because the similarity map repeats.
Inference pattern, like it's like a query, right? Query to the map you have already built. So like why it's called an inference pattern?
Oh, interference. Sorry.
Oh.
Did I say inference, or did I? Maybe I didn't speak clearly. Interference, yeah. So if you have the way to get unique representations using this scheme is you can take those vectors that are 120 degrees apart as sort of a module in your phase matrix and compute different rotations and different scales of that module and stack them, concatenate them to create a big phase matrix. And so now your interference pattern is the interference pattern of many grid patterns that have different orientations and different scales. And the result of all that is a nice similarity map that has a nice single peak, so we can uniquely represent variables in this coding scheme. But within this SSP, it kind of contains these grid patterns. And so if we represent these SSPs with a neural population, it's possible to set the weights such that we have a set of grid cells with grid patterns at different orientations and scales that represents the resulting SSP. And if you represent variables in this way, you can more accurately decode out the underlying X value compared to some directly encoding that X in a neural population or compared to some other more random SSP encodings. Yeah.
Can I just want to ask, so I think it might be helpful to explain a bit how you go from the abstract representation of the VSA to an actual encoding in neurons, because I think a lot of people are more familiar with like building stuff out of neurons.
Yeah. So, there's different ways of doing it. So with all of the work I'm presenting here, this is based on the neural engineering framework. So a neuron, my neurons could have various activation functions, but generally I use leaky, integrate, and fire neurons. And if a neuron's part of a population represented this SSP 5x, then that neuron's tuning curves, its rate over space, will be proportional to the dot product between that vector it's representing and some encoder vector you can think of it as the preferred input of that neuron in some respects. And so getting these is about setting those encoder vectors in a particular way. I don't want to go into too much details about like introducing the neural engineered framework, because there's also other ways you could encode vectors in spiking neural populations. But if you're interested in details of this, or if maybe there's interest in like learning more about like Mango and the NEF, I could, maybe do a casual tutorial about that at some point. Are there any questions about that at this point? Okay. All right, but in this framework, we can use SSPs in. You could also just represent it into a normal neural network. It's true, and just have represent the vectors directly. And then to get grid cells, you can set the weights on some next layer in a particular fashion. So here are some examples of neurons from spiky neural networks that are represented in SSPs in different ways, and you can simulate things like grid cells, place cells, object vector cells, and border cells. In these figures, I have a point X, I'm represented as an SSP that's moving across space, corresponds to this gray line, and the red dots are locations at which a particular neuron in a model fired. You may notice from these, I now have an X that I'm encoding that's changing over time. It's following this trajectory. You could model this by just having some XY value and just encode it as an SSP at every time step and plug that into your model and do stuff. But that's not very biologically plausible. Animals, say, moving, following some trajectory through space, they don't have some organ that tells them this is your XY location, Euclidean space at this moment. It would make more sense that if you had this high-dimensional representation of its location, that it would do updates to modify that over time in that high-dimensional space, in the neural dynamics. And if you try and do that sort of updating using self-motion cues, estimates from, say, optical flow or motor commands, that's the problem of path integration. Keeping track of your location space using motion. And you can do that with SSPs by just looking at if we have an SSP representing a time varying X, what are the dynamics of that SSP of this high dimensional representation? And it turns out the dynamics are that of independent velocity controlled oscillators. You can see that maybe with this sort of picture here, we have some X that's following a path through space. Its dot product with the different rows of the phase matrix, are going to be slowly changing or smoothly changing. And so the angles of these phasors are changing. So the phasors will be moving around, rotating about the unit circle in the complex plane. And their frequency, will depend on the dot product of the rate of change of X with the row vector that corresponds to that phasor. And pictured here is, if you're following some spiral path, this is how all the phasors, some SSP representation, are changing. I do have in the slides like a derivation of this, and it looks long here, but it's actually not that complicated. But in the interest of time, I don't want to go through it line by line here. But if there's interest, I can return to this, or you can just refer to the slides and maybe talk with me about it later. But given this, we can now easily create a model of path integration using SSPs by having sets of recurrent neural populations that basically realize these dynamics of each of those phasors. So we'll have neural populations that have these controlled oscillatory dynamics. And also my models, I add attractor dynamics to these systems to help stabilize things and make them more robust to noise. And the result is you can get a system that can perform path integration quite accurately for long periods of time. The degree of accuracy really depends on how many neurons you use to realize those dynamics of those different oscillators. Here I'm using quite a large number. I think I'm using like 1,000 neurons per oscillator. But if you use fewer, you'll see drift and error accumulation happen at much shorter time scales.
What were your actual inputs to that system?
The inputs is the rate of change of the position space. Yeah.
But you
Derivative.
recorded that how you're just getting those values from.
Oh, for the simulation, I have random trajectory, or in this case, actually it's from a real animal, with some data, and I'm using finite differences to get some velocity. In a real neural system, you'd want to do some mixture of like seems like animals use for path integration both internal motor commands and also things like optical flow and the perceptions of self-motion to get self-motion estimates. But in reality, it comes from several different systems, and these estimates are combined. And likely there's more intelligent like weighting of different estimates based on what's most accurate in a given circumstance. So the real story, if you want to model everything fully, is always more complicated than
Basically, you integrate velocity of the motion.
Yeah, exactly.
So what are the semantics of SSPs into that path integration?
The semantics of SSPs?
Yeah, that application and path integration.
Can I ask what you mean by that?
I mean, like you use SSPs as like VSA, right? So I don't really clearly see the connection for that application to the original VSA.
Yeah.
Because initially you talk about this VSA and also this
Yeah.
like semantic,
Yeah.
Now I'm confused.
Yeah, it's true. It's a bit different because VSAs, I talked about them, the sort of history is representing these discrete symbolic structures. But now I'm saying they can actually be generalized to represent continuous variables that have dynamics in neural populations. Just kind of a different application. What's nice about that is that it's be connected with that earlier work I described. You can, for instance, have a, as you're moving through space, you can use your estimate of self-location and observations of objects to get estimates of their location in space, and then bind that to a representation of the objects and store that in memory, right? Maps of environments.
I also depend like SSP is like it's a wave, right? It's a wave defined in a hyper like dimensional space, right?
Yeah.
Is it like standing wave or it's just like propagating? I mean, I'm talking about this boundary, right?
Yeah.
Obviously, you have this like, the space angle which is limited.
Yeah.
So
yeah, I mean.
So what range you use?
Yeah. So the phase matrix. So use terms that have various magnitudes. So you'll have waves at various scales. Those are parameters you can define. What's the range? You can still, though, even if it's a fixed range, it can represent points very accurately over space as long as you've enough components. And you have a little video here of path integration in action, where a gray line is some ground truth path, and the dotted black line is the model's estimate, which is just obtained by the maximum of the similarity map. So it's like a maximum likelihood estimate. And plotted here, the spiking activities of neurons that are doing the dynamics of each of these oscillators, and then what's being represented by those neural populations. So this actual value of the oscillator is just linearly decoded from the activity of those neural populations. And here I'm using fewer neurons than in the previous example, so you can start to see it near the end of this that there's accumulation of some noise.
So I can ask just to clarify here. So you have the X and Y deltas basically along the path.
Yeah.
And then you have, I assume, like an X vector and a Y vector, like in space, or how do you represent? Like you have this delta X and delta Y. And now you somehow use this to update the representation of location in space, but that representation does not use X and Y coordinates, right? That is this like interference pattern of these at different scales.
Yeah.
But so how do you actually do the path integration here? Like that part
The main thing the oscillators need is they need the frequency, the control frequency, which will be related to the dot product of the velocity with the phase matrix. So we really don't need to represent actually the velocity directly. We need to represent the velocity projected onto this phase matrix, and that's the input to the system.
Okay.
Yeah, and one nice thing about this is that actually these neural populations doing these dynamics, they don't depend on the phase matrix or even the dimensionality of the underlying space. You just have some number of them. That's the dimensionality of the SSP, and you could have this theta of X dot. You could have this come from different sources that use different thetas that have maybe different spatial scales, or are from computed using different velocities that perhaps are from spaces of different dimensionality. And these could all just be projected into this neural population. You could gate, which input is used and do path integration in different spaces and swap. And so it's fairly like, reusable neural populations that are doing.
Or combine multimodal.
Yeah, exactly. Yeah, that's also very doable. So if you have these, they're useful for doing dynamics in various spaces. All right. So other VSA applications. So now I'm going to talk about a few different models and things that have been done. I won't be able to go into all the nitty-gritty details for all of them, but if you're interested in any of these, please ask and we can stop on a slide and go into more detail. SSPs can, I've so far talked like in terms of spiking neural network models of representing space with SSPs. You can represent any continuous variable. You could represent frequency or shapes, or you can represent time. And if you actually add time to the path integrator, that's the same thing as having fixed baseline frequencies and all your oscillators. And you can apply integration on top of this to have, a memory of a trajectory, for example. It is kind of noisy. Maybe not the best way to represent a trajectory, spike in neural population, but it is one way. You can also use SSPs to do SLAM, simultaneous localization and mapping. So this is what I was talking about earlier. This is like kind of where this stuff combines with some of the other aspects of VSAs. This is a model that basically combines the path integration module, as I discussed, with a heteroassociative memory network that learns to associate representations of objects, which could be like bounds, like structures of different types and shapes and features. Learns to map that to the object's location in space allocentrically. And that can be obtained using the output of the path integrator. So as you move through space, I have a sense of where I am in this building as a whole. I have a sense of where that table is, how far away from me it is, what angle, the direction it is away from me. So I have a sense of where that table is in space overall. And now maybe I can, remember where it is even when I'm not observing it. And if I get lost and confused in this building, and I only for some reason can see a table and I re-encounter it, then I'll know where I am from recalling it. So you learn this heteroassociative memory network using the output of path integration as well as perception systems, about depth estimates. And in turn, that can be used to provide corrections to the path integrator to account for the accumulation of errors that would naturally occur without any form of correction. And here's an example of that where I have again here a ground truth path, the model's location estimate, and on the right, I have all these little simple just point landmarks, this little toy example that it's learning their locations and it's a source of memory network. At every point in the point of time, which it currently is, I'm taking the memory network and I'm querying for all the landmarks that have been observed so far. So you can see landmarks that it's observed near the beginning, and maybe only once or twice. It's not forgetting them. Those associations are being preserved.
Does it always know where the landmarks are, irrespective of how it's moving though? Like, so the little dot just happens to just have the knowledge of where all the landmarks are all the time? Because obviously,
it has
essentially you would be able to see landmarks if you were looking generally, but in this case, does it know where the landmarks are? Or does it only know where they are when it can see them?
It has like a field of view, a fixed field of view, and it can observe where they are relative to it when they're in that field of view.
What are the two sides there again?
This is the localization output of the model. So the dotted black line is the model's estimate of the path over time, and the gray line is the ground truth path. On the right here, these little X's, which you can't really see that well, are the locations of landmarks that have appeared within its field of vision so far. And the colors, the fuzzy colors, are heat maps from querying for each of those landmarks from the map. And I'm plotting the queries over top of one another.
What are those dots on the left that are moving around along with the location?
Those are noise. Those are that's some noise and interference in the similarity map. You can see that even though there is this, speckling, this noise, the maximum similarity value still follows the ground truth path. So the maximum similarity is maximum likelihood estimate. It is still accurate. Yeah.
And the memory of the system, it's just the current state, right? It's like the memory about the location, these interesting points, right?
Yeah.
That's just the current state of the system.
It's
like a recurrent state in a way.
It's not a recurrent memory. You can do that, but that won't be as accurate for as long.
Okay.
This is instead basically the map is stored in the weights of a network.
Oh, so it updates the weight.
Yeah. So there's learning rules that are going on here.
Hold on a sec. I'm curious what Florian thinks of this too. And what's the sensor that this virtual robot has? What sensor does it have?
Here, I'm just using an environment where I'm assuming I can get, if it's within some distance of objects, I can get some noisy estimate of depth or a depth estimate that is represented by in a noisy way by neurons. So this isn't a full like a robotic, a simulated environment.
It's not a robotic SLAM pipeline like the car has, right?
No, there is work on integrating this in a simulated environment and using vision sensors to get using vision using like convolutional neural networks to get the input the model requires. But that's sort of like work in progress. So.
But I think what you have is not far from a 2D LiDAR.
So you could use LiDAR to get that exactly what you need.
2D and you have some field of view. Get the basically distance.
You get a range factor basically.
Yeah. You could use either LiDAR plus
IMU.
Gert. And gyroscope.
Yeah. Oh, for the velocities, yes. You could use that, and then plus you need some sort of object classification system, or landmark classification, or some sort of way of getting.
You have to classify the landmarks.
Because it's learning a map of landmarks to their locations. Some SLAM systems, spiking SLAM systems, will learn associations between self-location and view representations, which are much easier to obtain. But then you don't get a map that can be queried in sort of nice ways after the fact, that this Alice-centric cognitive map. But if you want that, now you need more sophisticated input to the system. This is more like a semantic SLAM system. There are deep semantic SLAM systems which use CNNs to obtain this needed information. And this is a spiking version, though it doesn't have a spiking, vision systems to get all of that input that's not implemented.
I guess what Tommy was asking, like the camera you would only need if you want to learn the identity of the landmark. Right?
Yeah.
If you only wanted to know there is something here, there's also something there. You don't need to classify, right? Like the landmark would be enough in principle.
Yeah, you could do that as well. You need to slightly change how you do the recall to do the relocalization. But you could do that, yeah. Yeah, I do have a
quick question. So
Yeah.
how memory intensive or compute intensive was that simulation? It ran on Mango, I assume?
Yeah, on Mango, around my laptop.
Okay.
Not too long.
Have you quantified how much memory it took or much resources it needs?
I don't know off the top of my head.
Okay, that's fine. Just want to know.
It's like the total number of neurons. It's like in the tens of thousands of number of spiking neurons.
So technically, this could be ported onto a hardware, like a custom hardware. Which maybe don't need to.
I mean, I'm more curious why, these robot perception pipelines, SLAM is considered kind of the solved problem in robotics, right? Because it works very effectively at real time at a sample rate of 50 hertz on a 10 or 20 watt computer on a vehicle. So what would be the advantage of doing it with this methodology? What would you get out of reworking this well-established pipeline?
Yeah, I mean, my motivation for this was not actually robotics, really.
Is it computational neuroscience motivation?
Yeah.
Okay.
That's what I was more interested in. It was a potential application for the way in which maybe an hippocampal formation and the entorhinal cortex, that you could have a path integration model and you could have an associative map system that's used for correction and such. And I'm also interested.
Is it more interesting in an open world environment where you constantly have to form new maps as they explore new environments?
Yeah, it could be used in that context. That's sort of like that simulation environment. The current work, like the new work, is sort of going in that direction as well, of having multiple maps. But yeah.
Could it be much more parallelizable in theory than the SLAM? Could it be more parallelizable than SLAM? Because SLAM has a certain limitation in parallelization.
I will say, I feel like, to be honest, I feel like if you want to do SLAM as accurately as possible and you don't care about biological plausibility, you should probably use one of the existing pipelines. But if you care about maybe a biological plausible SLAM system that's using, neural things that are representable in neural population, and it's using, local learning rules to learn its connections, then there are SLAM models that are biologically plausible, things like rat SLAM and neural SLAM. And there's a whole family. They're all very similar to the original rat SLAM. But those, you don't learn a map that can be queried in this way. You can do fairly accurate localization over long time scales. But there's some components of that model that aren't so possible. And you learn just to represent associations between views, where you take some like, camera and you do some, you convert it to a grayscale image. Oh, yeah. Oh, fine. Okay, I won't talk about rat. I won't explain rats then. But look at this. You do things like after the fact, not just query for particular landmarks. You can query for landmarks that have certain features based on how you built your representations. You can also do sampling. Sorry. I'll do my transition. So I've talked so far about applications in spatial domains, but SSPs can also be used, and fractional power encodings can be used in non-spatial contexts. For example, going back to the probability distribution embeddings, you can use spike in neural populations to, given these vectors, sample from them by having a recurrent spiking population that has Langevin dynamics, essentially go in the gradient of probability given this embedding. That's fairly easy to compute, and add an additional noise term to explore the space.
So you can do the delegate pathfinding essentially, right?
You could do pathfinding, yeah, if you had like a distribution over paths and you want to sample paths. Yeah. Or
like the closest path, like the optimal paths or close to optimal, like without optimal.
Yeah, if you had like
exploring space.
If you had like a score function defined over the vectors, you could do that, and that's also work that me and Michael have been doing Bayesian optimization using these representations, and doing where you have some reward function and you encode your samples, like which could be trajectories in the space, and then optimize. You can also do things like represent images and do some queries to get relationships, query as follows, different spatial relationships between objects. And also in the last 2 years, VSAs have been related to transformers and attention and integrated in various ways because of course. And the most popular examples is HRR former, which Michael mentioned. This provides an alternative form of self-attention in which you basically bind your keys and values, and bundle them, and then you query. With your query vectors to obtain some similarities and do a softmax, and these become your attention weights. But recommend checking out the paper if you're interested in that. And there also are some alternatives. This Lars VSA, which is also provides some attention system in these VSA spaces using a binding and similarity of these vector representations. And it uses a learned projection from objects into the vector space. And it's sort of about learning these symbolic relationships between objects and then using that for simple reasoning tasks. And there's another model that was applied to graph classification. And another cool resource is this thesis from Zurich, I believe, that did in-memory VSA computations, and they applied it to tasks from like hand gesture recognition to feature continual learning, and they did hardware implementations of some of their algorithms. So there's lots of things you can do with VSAs, and if you're interested in using any of this stuff for your projects, and you have questions,